Welcome to Side of Science.
With Stacey and Ant, because every story has a side of science.
On today's episode, we're talking about radiation. Hi, Ant.
Hello, Stace. What's going on?
Not much. Yourself?
Well, I've been writing a lot of content on radioactivity and radiation.
Oh.
And so I thought we'd talk about radiation, what it is and what it isn't.
Oh, exciting.
Okay, so let's start off. Stace, what is radiation?
I'm just going to give you my definition of what I understand it to be, and that's ionization.
You're very close. So radiation really just means energy emitted or energy traveling through space. So it usually comes from an atom. There's a couple of different types that we talk about. The really, I wouldn't say simple, but the one that everyone will have experienced is your electromagnetic waves.
And that includes things like light,
microwaves, radio waves. We're getting bombarded by this type of radiation every day. X-rays, gamma rays, your entire electromagnetic spectrum are a form of radiation which doesn't have mass. It is a wave or a photon, depending on which model you get into. The other type is the one that anybody who's played Fallout or watched anything which some post-apocalyptic mutants will have heard about is radioactivity or radioactive decay. That's a type of radiation emitted from the nucleus of an atom. But radiation really just is an umbrella term that talks about energy emitted from an atom that travels through space. So is radiation bad for you, Stace?
Well, I would say, from what you've just said, that the first part, your light wavelengths and those, not necessarily. I mean, in high doses, an X-ray is going to be bad for you, but no, not. You'd need something like 18,000 X-rays before it's going to do you.
You need to break a lot of bones,
it's
you're probably in a lot more trouble
damage
already.
But that nuclear radiation is terrible for you.
That's the one.
I've seen Chernobyl.
Good show. Very good show. I actually watched it on the weekend. It kind of sparked this. So this is actually a really good point because essentially there are two types of radiation, whether it comes from the nucleus or whether it comes from electrons, electromagnetic spectrums, ionizing and non-ionizing. Non-ionizing is harmless to us. That is the one that we can use freely. And essentially that radiation doesn't have enough energy to cause electrons to escape the nucleus.
Okay. So this is my light, my radio, my microwave, my mobile phone.
Yep. If you're looking at the electromagnetic spectrum, let's deal with that stuff first. Everything up to UV.
Yep.
So light, heat, all the ones that we use for communication. Your mobile phone uses microwaves. Your phone also uses radio waves. The radio in a car. They're non-ionizing. That means that electromagnetic wave is not carrying enough energy to cause any electrons to escape the atom.
Okay, so no damage.
No damage. So once you get past UV, X-rays and gamma rays, they carry enough energy that electrons will start to escape the atom. And they're called ionizing radiation.
Okay.
They're the ones that we typically think is bad for us. And when you're talking about radioactive decay or like radioactivity, uranium and all those scary things, they can be ionizing radiation. They essentially are ionizing radiation. There are three, we'll really briefly do this, three types of radioactive decay in terms of like uranium, plutonium, all those radioactivity. Alpha, beta, and gamma, they are all ionizing. So they can do us damage.
Okay, and so something like UV?
UV, why do we get burned from the sun?
Yeah.
If you spend too long in the sun, UV radiation is ionizing. It will take electrons from the atoms in your body and you can get sunburnt, and long-term sunburn can also lead to cancer and all sorts of other things.
Right. No good.
Not good. So ionizing, not the best for us. Non-ionizing, completely harmless. We use those every day.
So what does ionizing radiation do to one's body?
Okay, so let's go back to the structure of the atom, a classic Bohr-Rutherford model that we teach high school kids with our nucleus and our electrons orbiting in different shells.
Yep.
The different shells that electrons orbit in correspond to different energy levels of electrons. Now, electrons can jump between shells.
Yeah.
If an electrons can absorb radiation. So if
they get excited, they jump.
Exactly.
How do you get it excited?
Well, it's got to absorb the right energy level. So different radiations come in with different energy levels. If it absorbs a certain amount of energy, it'll jump a little bit. So a low like electromagnetic wave at the right frequency might cause an electron to jump up 1 or 2 shells.
Where is this energy coming from?
Well, from other forms of electromagnetic waves, other sources.
Okay,
So
so
let's-
light energy could excite an electron and get it to move up.
100%.
Okay.
So we're kind of getting into what we call light production here. So in a nutshell, energies can jump up levels.
Yep.
If they jump up levels, they don't stay there permanently. Eventually, they will drop back down to their original level. And do you know what happens when they drop back down? They emit a form of electromagnetic radiation. So that's how light's
you
actually...
see it as light, yeah.
Or light, or heat, or radio waves, or gamma rays, or any of these other forms of electromagnetic. So that's essentially how the electromagnetic waves are emitted, and also how electrons can jump between different shells in the Bohr model.
So if you've got an outer shell electron that gets really excited,
Oh, yeah.
where does it go?
Leaves the atom completely. So that's called ionization. The reason it's called ionization is because if I have a neutral atom with the same amount of protons and electrons, protons being positively charged, electrons being negatively charged, they're balanced. If I remove an electron,
Which is negatively
which
charged.
is negatively charged, my atom becomes
Charged.
positively charged.
Yeah.
It becomes an ion, a positive ion. And the reason those are bad for us is that atoms don't like being positively charged ions on their own.
No, they want to be stable.
They want to be stable. So how does a positively charged ion become stable in your body?
Well, it's going to need an electron from somewhere.
It's going to need an electron from somewhere, and it becomes really reactive. It goes around your body searching for atoms to bond with or react with. And some of the atoms it's going to find to react with include your DNA,
Yep.
your cell membranes, and the proteins in your body too.
Definitely.
And once you start disrupting these, what can happen as a biologist? I was hoping you could shed some light on this.
So if your DNA is impacted, then you can start to get mutations.
Yep.
And so these mutations can manifest as uncontrolled cell growth, which leads to cancer formations. So that's probably your big one.
That's the big one. And that's what I think everybody knows about the dangers of being sunburnt and staying out in the sun too much and skin cancer.
Yeah, long-term impacts.
Yeah.
You're affecting your DNA, and this can mutate over time to increase your risk of cancer.
Yeah, perfect. And so the term, which I think a lot of people would have heard this term, the other term that people use for these ions are called free radicals.
Ah, yeah. Anti-who? Do you remember that ad? Anti-who. Sorry. It was-
Anti-who. Yeah. And the thing that helps counteract free radicals,
Antioxidants.
antioxidants. And where do we get antioxidants from?
Food.
Food. Things like tea. I remember seeing all the ads. Chocolate's good for you because it's got antioxidants. I've used that one many times.
Vitamin E, vitamin C. Yeah.
All forms of antioxidants because they will bond with the ion or the free radical before it has a chance to hopefully bond with other molecules in your body like your DNA. So that's why free radicals are bad, and that's why antioxidants are good.
So in the case of Chernobyl,
Yeah.
we've got a nuclear reactor
Yeah.
that gives off radiation, and a whole town has to be evacuated in, 1986?
1986, more than a whole town.
People still don't live there.
No, 2,600 square kilometres had to be completely evacuated. The soil had to be removed. All the animals had to be shot. Everything had to be burnt.
And this is all because of radiation.
This is all because of radiation. So this is when we get into our nuclear radiation, or radioactive decay. And this is the alpha, beta, gamma stuff I was talking about earlier. So your electrons jumping shells will release our electromagnetic waves, and they can be harmful, like UV, X-rays and stuff, in high enough doses. The real issue with your radioactive decay is that your radioactive decay will continue to emit radiation. So once your electron jumps back down, it releases a photon or a wave, and then it's quite happy until it absorbs another photon or electromagnetic wave and decides to jump again.
Right.
But your nuclear decay occurs continuously. And so
Or for a long time.
for a long, long time.
A long, long time.
Yeah, a long, 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 long time in some cases. Well, some are really short. So let's go really briefly into nuclear decay. atoms can become unstable when they're too big. So anything past polonium onwards,
So anything with an atomic number larger than 84.
correct? 84 and above, they're too large. The nucleus of them, there's too many protons and neutrons to be stable.
Right.
And so the way that they become stable is that they radioactively decay. So
And that just means they're losing electrons.
they're not losing electrons, no. So radioactive decay comes from the nucleus. That's why we call it nuclear energy. So your electromagnetic waves, they'll come from mostly from your electrons jumping up and down. But now we're talking about nuclear energy.
So this is your fission or your fusion.
They will release energy from the nucleus as well, but that's not actually what we're talking about. So that is nuclear energy. We're talking about radioactive decay,
Okay.
which is the nucleus being unstable and decaying to try and become stable. Let's use a bit of an analogy. Everything in the universe is lazy. It wants to be in its what we call lowest energy state.
Inertia? Is that what you're...
Yeah,
Yeah?
inertia. Students as well.
Yeah.
Like if a student can do nothing, a student will do nothing.
Yeah.
And a student will try and get back to doing nothing at all costs, right? The same thing with a radioactive element. There are actually 3 different ways it can be unstable. It can actually have too many protons, too many neutrons, or be too large. But that's a really big rabbit hole we'd go into.
Okay.
The way an unstable nucleus becomes stable is by emitting either an alpha particle, which is a helium nucleus, so it's trying to make its mass smaller until it becomes stable, or it can emit a beta particle, 2 different types of beta particle, or a gamma wave, which is an electromagnetic wave. Essentially, it wants to emit things from the nucleus until it becomes stable.
And then it can go back to doing nothing.
And then it can go back to doing nothing like our lazy student. And that's unfair. A lot of students are very, very motivated. A lot of students are very radioactive and they want to do things. But the radiations and the particles and the gamma rays that it emits are ionizing. Now, an unstable element doesn't just emit one nucleus and be done with it. Often it will still be radioactive, just in a different form, and that will undergo radioactive decay. The other thing is, there's more than one atom in a sample of rock. So if you have a uranium sample, it contains billions and billions of these atoms.
And they're all going to decay.
And they are all unstable, and all of them want to become more stable by decaying.
And once they've gone through that once, they're still unstable, so they have to do it again.
Most of the time they are unstable. And so that's where we get our term half-life from. We can't predict when an actual atom is going to decay. If we have 1 million atoms in a sample, we know that they will decay, but we don't know when. So a couple might decay now, a couple might decay in another second. They're constantly firing bullets,
Yep.
right? And so the half-life is how long does it take for half the atoms in that sample to decay? And so your half-life for some of these elements like plutonium and uranium can be in the tens of thousands of years.
Right.
So
So we're not going back to Chernobyl.
we're not going back to Chernobyl
for a long
for
time.
thousands of years because you have these unstable elements still in the soil, still emitting radioactive decay, which are like bullets. They're ionizing radiation, and once they hit your body, they can start causing pretty bad damage.
And so if they hit your body, it's going to be an acute radiation sickness.
Yeah, good. So it depends on the dosage. The same thing is like being out in the sun on the beach, right? I can go out in the sun with no sunscreen on a 30-degree day for 15, 20 minutes and I'll be fine. But if you stay out there for hours, you're absorbing more of the radiation, you're going to start to get sunburnt, you're going to start to show effects. And if you do that every day for the rest of your life, well, then you're going to create more free radicals, which increase your chance of getting things like cancer.
Yeah.
And so that's the same thing with your nuclear or radioactive decay. If you're exposed to a little bit, it can cause you a bit of damage and it could slightly increase your cancer. I mean, our body's really good at repairing itself too.
Yeah, because you would be exposed to little bits of these alpha, beta, gamma from medical treatments if you needed them, right?
Oh, we are radioactive ourselves. So
Alpha, beta, gamma?
yeah. So isotopes are different forms of the same element. So you have isotopes of hydrogen, which just have a different number of neutrons. Now, some isotopes of almost every element are slightly radioactive. So if we take potassium, for example,
Yep.
the main form of potassium we see is not radioactive. But there is an isotope of potassium that's very slightly radioactive.
And this is why bananas are radioactive.
This is why bananas are very slightly radioactive. So your tiny little forms, you're being exposed to bits of radiation all the time from radioactive decay.
Okay, so if we're going back to the bananas,
Yeah.
if I eat a banana every day and it has radioactive isotopes of potassium,
Yep.
I could be getting doses of radiation, but hopefully I'm also getting enough free antioxidants that I'm combating this effect.
More than enough.
Okay, so I'm not going to die by bananas. Okay.
An overdose of banana is not going to kill you from the radiation. There might be some other side effects from eating that many bananas. So we can measure the exposure to ionizing radiation in a unit called sieverts. And the average person is exposed to about 2.4 millisieverts per year. And that's completely safe and normal. It means nothing.
What was Chernobyl exposed to?
Well,
give me some reference. Or
to give you an indication of what the difference is, that was a millisievert, right? So that's 1,000th of a sievert. Above 1 sievert, you're going to start to get acute radiation sickness. So that's almost 1,000 times more than your average exposure a year.
right.
Above 4 sieverts, without treatment, 50% of the people die pretty quickly. Above 8 sieverts, nearly 100% fatal, even with medical intervention.
How quickly?
Well, again, that depends on how quickly you're exposed to it. So to put it in perspective, in Chernobyl, right, many of the first people on the scene were the firefighters and first responders. And they were exposed to 14 to 16 sieverts over a very short period of time, in minutes to hours. And so if you've seen the movie, that's why they're throwing up almost immediately. They're getting there and they're getting a shotgun of radiation.
There's not enough.
There's not
Antioxidants.
enough tea in China to save them at that stage.
Yeah, wow.
So essentially, they were exposed to over 200 to 800 times the limit that we would get in a year in a matter of minutes or hours.
And so it's interesting then the symptoms that they have from this acute sickness.
Yep.
So things like your vomiting,
Yep.
obviously long-term cancers, but I guess more immediate would be similar to something like radiation therapy for cancers.
Yeah.
Assuming these.
So the levels are high enough that their cells are actually starting to be affected. The cell membranes are starting to die.
Yeah. So radiation and the free radicals can target cells that are rapidly undergoing replication.
Mitosis.
Yeah, so they're actively dividing. So these kinds of cells are things like your hair,
Yep.
which is often why your hair falls out, your stomach lining, which is why you feel sick and get nauseous.
Yep.
And that's kind of mirrors that. Is that fair to say?
Yeah, and that's kind of one of the treatments for cancer is radiation therapy.
Yeah.
And for some cancers, particularly tumours,
Because cancers are fast growing.
they're fast growing. They will insert a very small radioactive sample in a person and they'll shield most of it and just have the radioactive particles directed at the tumour, and that will start to just locally kill the tumour without really affecting the rest of the body.
Yeah, right. So that triggers apoptosis and the cell undergoes cell death.
Undergo cell death. So it is all about the dosage. So
The dose maketh the poison.
So I know I've been talking a lot, Stace. It's been pretty in-depth, but how could we bring it back to a classroom?
Well, this is useful for, obviously, radiation. I'm not a VCA physics teacher, so I can leave that, which is good. But I think it's really interesting, too, to talk about cell division and mitosis and how different cells are undergoing different processes and can be affected differently. So I could use it there. And then, obviously, your radiation and nuclear stuff for your middle years.
Yeah, direct. It's in year 9, year 10, your radiation and nuclear stuff, and physics as well. But I really found the free radicals and the biology side really fascinating for me in terms of it increases your chances of getting certain things, and it doesn't affect everyone the exact same way. It is a bit of a game of Russian roulette sometimes with radiation. But to kind of bring it to a close, radiation, bad for us, Stace?
Depends on the dose, depends on the type.
It depends. It really does. And the funny thing is, without electromagnetic waves and radiation, we wouldn't be able to live our modern lives.
No, the sun. You need the sun for life.
We need the sun. We need Wi-Fi. And without microwaves, we do not have Wi-Fi.
I can't argue with that.
Thank you for listening, Stace.
Good chat. Thanks very much.